I'm Anil Kumar. Welcome to my YouTube channel and the website Global Math Institute. We'll now discuss about relations and functions. In this video, I am going to talk about the relations, types of relations, mappings, functions, test for functions, function notation, domain range, and as we go along, we will have a question to review the concept. Now, these are very important topics to begin with, and they are foundation for higher level mathematics. And therefore, in most of the books, whether you are working in O level, A level, AP, or IB math, functions and relations is always the very first chapter. So we need to understand how these terms are related, and then we'll move forward to the other related areas. Relations. I always begin with the basic relation, which is my mother. All living beings will have a mother, right? So it is a relation which is relating everyone to their mother, right? So it could be shown as an arrow diagram. We also say kind of a mapping diagram. Now you realize that two or more persons can have one mother, right? So what we see here is that, well, the relation is kind of like this. However, we could have many related to a mother also. Right, so this becomes a relation in which we are relating many to one. So when we say relation, that is a relation. In this world, everyone and everything is related. We need to define the relation all the time. And types of relation, I think you got an idea. We'll get into details later. Right. So what you see here is many are being related to one. Right. Now when we say mapping, sometimes the word mappings and functions are used as same terms. In many parts of the world, we kind of look into this set as one set of items and the other as another. And that relation, when shown in the fashion shown here, is called a mapping diagram. Now in this mapping diagram, we will refer to these as our inputs, and what we get here is output. We might also refer to them as objects and their images, right? In general term, right? So objects and their images. And technically, when we talk about functions, we'll refer them to as domain and range. Right. So that is the technical term which we are going to use, where domain is set of these. And what are these? These will be referred to as elements. So all these, so let's call them like A, B, C, D, E. Let's call these as capital A, capital B, capital C, something like this. In that case, all the elements in the domain can be written in the form of a set. So this curly bracket gives you a set, and we can write this as list all these elements, right? So at present, we'll just define it to the terms shown here in the mapping diagram. So the curly brackets indicate set of elements. Right? And that set which we have shown you is actually the domain, right? So in this case, the domain is the set of elements. And the range will be the set of elements capital A, B, and C, right? So this set of elements will be referred to as the range. Now, in this particular mapping diagram, what we see is that every element in the domain has a unique association, right? There could be more elements associated with one, right? So more inputs can be linked with one output. However, any input is not linked with more than one, right? What I'm trying to say here is that if I reverse this operation, that is to say, think about another relation, which could be my child. So if I reverse this operation, my child, in that case, a mother, which is capital A for us, can be linked to more than one, right? So I'm just redrawing this, right? So in that case, this could be something like this, right? Clearly, what you see here is that in the domain now, those elements which refer to mother comes into picture. And since A is related with more than one, it still remains a relation, but it is not a function. Correct? So in that case, what we have here is a relation, not a function. Reason being that one element has been related to more than one, right? So when we say, when the mother says my child is a good student, we don't know which child the mother is talking about. Correct? So we are not specific. We have an ambiguity. So when we are not specific, it is very difficult to talk about it logically. And so it fails that logical test. And we still call it a relation. It is definitely a relation. However, we do not give it that special name of a function, right? So that relation is, as you can see, one to many. We'll further talk about these things as we move along, but that gives you kind of an idea of what we are getting into, right? So I hope that makes sense. Now here is a question for you, which says, provide examples of relations that cannot be defined by an equation. Well, the relation which we just discussed is very easy to talk about, but truly speaking, we don't have a mathematical equation to relate it, right? So it is sometimes easier to describe the relations in just words or in mapping diagrams as we have shown here. I hope that makes sense. Now let's move on and now take up each topic in details. So what we have learned is that everything is related, and relations basically two or more concepts, objects, persons, or points are connected. So when we say relations, we are actually relating objects or concepts as we did earlier. And as we move along, we'll talk more in terms of points, right? So now, as we move along, we will actually be writing the relations in the form of equations where we'll introduce variables. X generally will refer to the inputs and Y will be referred to as outputs or images. Now these variables X and Y makes our things very simple to talk about, And when we write it like within the brackets, x comma y, we'll call this as a coordinate point. And normally we can represent this on a Cartesian plane. So whenever we're trying to relate objects and concepts in the form of a mathematical equation, we can actually refer to them as some points in our coordinate plane, and these set of points will define the relation, right? So that is how we have, right? So we'll have a function which will be set of the coordinate points. So I hope that makes sense. So mathematically, as we move from relations to functions, we'll actually more and more like to write those relations algebraically, represent them as these coordinate points, and we'll call them a function and show them on a graph and then work with it, right? So that's the whole idea as we move along. Okay. Now let's further explore the types of relations. Let me divide this page into 4 parts. Since broadly speaking, there are 4 types of relations, I will now sketch simple graphs to represent these types of relations. We have already talked about 2 types of relations, many to one and one to many, right? Now, if I have a straight line, let's say we can have something like this. Let me form a cubic curve like this, right? Now, in this curve, every point is kind of connected, and when you connect them, you get a solid line. Do you see that? So when it is something like this, we are saying that along the x, we have put all our x coordinates, which is the domain of our function or the relation, and along y, we have kept the elements of our range. And when we connect them like this, show them with the arrows on the 2 corners, that means they will be moving infinitely large values in the direction shown. And a connected path like this says that both x and y belongs to the set of real numbers. So every element on our Cartesian plane is referred to a part of real numbers, right? Now what you notice here is that one value of x is associated with only one value of y. And therefore, we call this as 1-to-1 relation. Right. So the name of this relation is 1-to-1. Now if I have a graph which is, let us say, like this. A parabola opening towards the right, mathematically x equals to y squared, right? So mathematically I could write this as y is equal to x cubed, and this one I could write as, let me write, x equals to y squared. Now here what you note is that a value of x is related with 2 values on y. Do you see that part? And therefore, this relation where elements of x may be related to more than 1 is called 1-to-many relation. Perfect. An example of a parabola, which you know is a graph you get when you sketch the relation y equals to x squared. Now in this particular case, two values of x have the same y value. Do you see that part? Right? So in this particular case, you can say that many are related to 1, right? So many means more than 1. Is that clear to you? Now in the case of a circle, you notice that x values could be related to more than 1, right? And you also notice that the y value could be associated with more than 1 x value. So this kind of a relation is called many to many. So basically, there are 4 types of relations as shown here. One-to-one relation, one-to-many relation, many-to-one, and many-to-many relations. You can, of course, provide equations for all this. I could write this as x squared plus y squared equals to, let's say this here is 5, right? So I could write this as 5 squared. So this is the radius square. Gives you the equation of the circle. Now, we'll distinguish between relations and functions at this stage. You note that all these relations can be represented in terms of equations, right? So we do have algebraic representation. However, we see that 2 are special cases where every element of x is uniquely associated with y, right? So those are called functions. So in case of functions, it is necessary to see that every element is uniquely associated with one element in y. So we have every element in domain, we'll say, that is the x value, right, is associated or linked with an unique image. Now that happens in 2 types of relations. One is one-to-one and the other one is many-to-one. So these are the 2 relations which are also functions. The other 2 relations, one-to-many and many-to-many, are not functions. Is that clear to you? Correct? So that is a very, very important aspect as we move along for you to understand. So this is a function and this is also a function, right? So these are these 2 relations which we are talking about. Now you understand that most of the relations can be represented in the algebraic form, in the form of equations. We could also show them on a graph as set of coordinate points x and y. Looking at the graph, we can actually decide whether the relation is a function or not a function. Well, what you notice here is that if I draw a straight line, it cuts the graph at 2 points, and therefore these 2 are not functions. So we also call a vertical line test to check for our functions. It really means that if I draw a vertical line and if it intersects at 2 points, then it means it is not a function, right? Here if I draw a vertical line, it only intersects at 1 point, so these are functions. So vertical line test is a very simple test to check for functions when the graph is given to you. We'll further explore how do we figure this out when the equation is given to us. Now here is the second quiz question for you. Which type of relations are functions, right? So the answer is right there on the sheet, one-to-one and many-to-one, right? So I hope the concept is clear to you. Perfect. So let's move on and take the next related topic. Now let us further explore relations and functions. So we have already seen that relations can be described in terms of words, in terms of set of ordered pairs, and these ordered pairs can be written in the form of a table. We can represent them on a mapping diagram. We can sometimes write equation and also plot them as a graph. Let me take an example here, right? So we'll take an example. Let me define a relation in words. Let it be 1 less than twice a number. So that is a relation in terms of words, right? So that is how we are describing a relation, 1 less than twice a number. So in the form of a set of ordered pairs, we can say that if the number is 0, so now we have 1 less than twice 0. Twice 0 means 0 minus 1, so we get 1 as our output. Now if 1 is the number, twice 1 is 2, and less 1 is 1, right? If I have the number 2, twice 2 is 4, 1 less is 3. If I have number 3, twice 3 is 6, 1 less is 5. So these are the ordered pairs. Do you see that? Which represent this kind of a relation. We could have many of these, right? Now if I write them in curly brackets, kind of like this, it becomes a set. So when I say set of ordered pairs, so that is the notation. Do you see that? And if I write these dots here, that means infinite elements. You get an idea. Now the same relation can be also represented in terms of a table. We could write some x values here, and for each x value we'll have a y value, unique y value. If x is 0, y is 1. If x is 1, y is 1. Minus 1 in the first case. For 2 it is 3, for 3 it is 5, and so on. So that is the table of values which you have just seen, correct? Now the same set can also be represented as a mapping diagram. So let me show it in a mapping diagram. So we make two circles. One is for the domain, the other one is for the range. You're now familiar with these terms. We'll just write these 5 or rather 4 terms here, 0, 1, 2 and 3, and they are associated with minus 1, 1, 3 and 5. Linking them with an arrow. So arrow is kind of important to draw to indicate which is an object and what its image is, right? So that is how it is linked as a mapping diagram. We could describe this as a relation also. When we say 1 less than twice a number, the numbers are written in the coordinate points x and y, where we say y is equal to twice the number and then take away 1. So that becomes our equation, correct? And if I have to plot it on a graph, it is a straight line, as you know. And this straight line can be represented with these points connecting them, solid straight line, so kind of like this, right? So here we have x-axis, y-axis, the points, this is 0. At 0 we have the value of -1, right? At 1 we have the value of 1. Plus 1, and that becomes a straight line with all other points, as you can see, right? So 1 less than twice a number, right? So that is a graph for us. So this is the graph. So these are different ways in which we'll be representing our relations. Now the question is it a function? So for that, what are we going to do? We'll perform vertical line test. So if I draw a vertical line, then I notice that it only crosses the graph at one point, right? So if I draw any vertical line, it only crosses at one point, and therefore it is pass, success. That means function. So what we notice here is that every element in domain is associated with only or uniquely element in range. So there is a unique association, right? So it is 1 to 1. And therefore it is a function. So that is how you are going to describe whether the given relation is a function or not. Is that clear to you? So based on this, we have a question for you, which is right there. Explain why x minus y square is not a function. You can take your time. Now, there are a couple of ways we can do it. We can show it algebraically. So in that case, let me write what y is equal to. So y is equal to, we'll say square root of x. Whenever you do square root, you have to take plus and minus. It makes sense, right? Or you could also write as coordinate points. If I take x as 1, the y value could be -1 and could also be +1. Do you see that? Right? So basically, what we see here is that this set, one value of x is linked with two values of y, plus and minus 1. And therefore, it is not a function. You could also sketch the graph for this. The graph of this particular relation will be parabola, which opens on the right side. And this parabola fails the vertical line test. And therefore, it is not a function. So fails vertical line test. So these are different ways of proving that the given statement represents a relation but not a function. Is that clear to you? Perfect. So these are ways in which you could describe. So I hope it makes sense. Now let's move forward and take up different ways of writing our functions. We call it function notation also. So now we are going to discuss how do we really work with these functions. Now there are many ways in which we are representing these functions. Common ways are, for example, I could write y equals to, just as we said, is equal to 2x minus 1. So that is one way, right? Now every equation is normally written with y. It's a good thing to give it a name, and that is what function notation is all about. So basically we'll name our relations. Right. So general term is relations. You could use functions also. So we'll name it as f of x. Now specifically if I write f, it means a function, okay? So we could also write the same equation as f of x equals to 2x minus 1. So name our relation. So normally the names are any alphabets, lower case letters. Right. There could be other relations. For example, you could write y equals to x squared. You can write g of x is equal to x squared, right? So you could use any lowercase letter to represent your function. Does it make sense to you, right? Now another very popular notation is that the letter f for functions, right, with a colon, and the colon means such that, and we are actually linking x values with the function itself. So in this case it is 2x minus 1. Does it make sense to you? Right. Similarly, we could write that as g. The x values now are linked with x squared. So that is another popular way of writing a function, and this is also a function notation. So all these are function notations. Most of the time we'll prefer using f of x equals to 2x minus 1, right? So that is more elaborate way of writing. Let me write down what each symbol here means and how do we read it. So to read this, we say f maps. As I said, functions are also mappings, right? So f maps x on to 2x minus 1. Does make sense, right? So that is how we could describe it. We can also say function f is such that. Now this such that is for this symbol, colon, right? X is mapped to 2x minus 1. So you could also describe in this fashion, right? So that is a short form of writing. This is a short form of reading, and that is describing. Do you understand? So you could read as all this. So f maps x onto 2x minus 1. Is that clear to you? So you can describe the given function g maps every element of x to x squared. Perfect. So that is how these could be linked. Right. So we have the second relation. For example, if I am drawing my mapping diagram, in that case we could say that this is a function g of x. So g of x is kind of a relation which relates each and every element from the domain, right? So this is your domain, and that's your range. And this is such that if I write 0 here, it will be linked with 0, square of that number, right? If the x value is 1, it will link with 1, but if it is 2, it will be linked with 2 square, which is 4. You get an idea, right? So what you also notice here is that if it is minus 2, the square is also plus 4. So this particular relation is many to 1, right? So this again is a many to 1 function. Correct? So functions can be represented in the form of an algebraic equation in which we prefer to use the letters instead of just y. Right? So in function notation, we are replacing generally y with our name, which is g of x or f of x, where x is your domain, the variable, which is the object, and the relation is described on the right hand side, x squared in this case and 2x minus 1 in the previous case. So I hope you understand how to represent the functions, correct? Now based on this, we have a question for you, and that is, function is defined as 3 less than twice a number. Find f of 1. Find x when f of x equals to x, and find x when f of x equals to 9. I'd like you to pause the video and answer this question at this stage. Let us understand this very concept. So when we say function is defined as 3 less than twice a number, let's give it a name. Let's say f of x is our function. It is defined as equal to 3 less than twice a number. Number represented by variable x, twice a number, and then you take away 3. Okay? So that becomes your function. Now when I say f of 1, it really means replace x with 1. So when you do that, we get f of 1. So replace x with 1, so we get 2 times 1 minus 3. And this is equal to minus 1. So the value of f of 1 is minus 1. Perfect. Do you understand the concept? So that means this is equal to minus 1, as shown here. The second part of this question is, find x when f of x is equal to x. Well, that is an algebraic equation to be solved. We are saying f of x is 2x minus 3, so we'll say 2x minus 3 is equal to x. So we have to solve this equation now. 2x minus x equals to 3, and that gives you x is equal to 3. So here the solution is x equals to 3. Does it make sense to you? So these are the type of problems which we are now getting into as we move along, right? Now, part C here is find x when f of x is 9. So when I say f of x is 9, that really means that we'll replace f of x with 9. We say 9 is equal to 2x minus 3. We have to find the value of x. So do the reverse operation. 9 plus 3 equals to 2x, and that is 12 equals to 2x, and that gives you the value of x as 12 over 2, which is 6. So the value of x is 6. Perfect. So this is what we are going to do further once we represent our relations in the terms of functions, and then we can work around with them. So in this part of the video, we learned how to represent functions in the form of function notation. Basically, you can give name to every function so that we can communicate better about them. And these functions can be written in the form of algebraic expressions. And we can do a lot of working with these algebraic expressions as shown here. Correct? Now let's talk about domain and range of each function, right? Every function is restricted. They will have some domain and some range. So in the last part of this video, we'll now take up functions and we'll talk about their domain and range. As discussed earlier, domain is what? So whenever we say domain, we are saying the inputs. So we're talking about inputs to be considered. In simple language, and when we say range, then we are talking about possible outputs, right? So when we say possible, so we are actually qualifying these words with all inputs and all outputs. All possible. Do you understand? That is what domain range is. Now we'll talk about domain range with reference to different types of functions. So for example, let's take a graph. We'll actually plot 5 graphs here, and then we'll write down their domain range. Okay. So we could have a graph which is kind of a straight line. We could have a graph which could be kind of like this. We could have a graph which is like this. We could have a graph which could be like this. Or we could have a graph which is broken like this. Okay. All these are graphs of functions since they pass vertical line test. Now let us see how to write domain and range for these functions. Let's say this point here is plus 2, right? And this point here is also plus 2, but the x value here is minus 1 and the x value 1 on this side. Now to write domain and range, we say domain for this function here is that x belongs to real numbers. That means there are no restrictions, right? All values are allowed. And the range written by letter R will be y values. They all belong to real numbers. So the x-axis represents the domain, the y-axis, all possible outputs as range. Does it make sense to you? Correct. In this case, again, the domain is all real numbers. However, the range is restricted. And we say range is y does belong to real numbers. However, so that is the condition. We are saying y is less than and equal to the top value, which is maximum value of 2. Since the parabola opens downwards. Now here in the graph, the arrows indicate that they move infinitely large values towards right. So the domain here is x belongs to real numbers. However, you note that the center point is not part of domain, nor it is a part of range. So we have a restriction here that x is not equal to 0. Similarly, for range, we'll write y belongs to real numbers so that y is not equal to 0. So those are the restrictions on our domain and range. Do you see that? Now in this particular case, a square root function, we say that the domain is x belongs to real numbers where x is greater than equal to 0, since 0 is a part of our function. As far as the range is concerned, range will be written as y belongs to real numbers where y is also greater than or equal to 0. Perfect. Now the last function is kind of tricky. We have restricted domain range as shown here, and we have a piecewise function. Very special case. So in this case, let us say this value here is minus 2 and this value here is minus 3. Now we can say that the domain here is represented as a value in between minus 1 and minus 3, right? And then beyond 1, correct? So here we can say, we can write it in many different ways. So I'll use a shortcut method here since we have very restricted space. So we are saying here that the value is where x is greater than equal to, since this is a closed circle, minus 3 and is less than minus 1, right? And then we are saying, comma, it is greater than 1 and equal to 1, right? So since 1 is included. So we'll talk about it more later, however, that gives you an idea that it could be complicated. As far as the range is concerned, we could also write it in the form of brackets. We know this minus 2 is included, right? And in this case, 2 is also included, right? So all values between minus 2 and 2 are part of range. So we can say y belongs to real numbers where the y value changes from minus 2, right, included, and 2 included. Do you see that? So that is how we could write the range for the given function when it is given in the form of a graph as shown here. So that gives you an idea about domain and range. We are actually going to explore all this in the next video, right? Now here is a test question for you. You are saying, find domain and range of the function f of x equals 2x minus 3 whole square minus 2. One way is to sketch this function, and from the graph you can write down. So the graph of this function is a parabola which has a vertex at 3, minimum value is at 2, right? So its value here at 3 is minus 2. So let's say this is the point 3 minus 2, right? Sorry, 3 is here. 3 and minus 2 will be here, right? So sorry, that's not the point. So this is the point which is 3 minus 2. Now, if I write 0 here, in that case, we get 9, 3 squared, minus 2 is 7, right? Somewhere there, right? So we have a parabola which is kind of like this, where the minimum point given to us is minus 2, which occurs at 3, of course. Now from here, we can write that the domain for the function is x belongs to real numbers. As far as the range is concerned, y belongs to real numbers. However, y is greater than equal to minus 2. Correct? So from a given equation also, you can write domain and range. You may have to sometimes sketch a graph or work out a method. There are so many different ways of finding it, which we are going to explore in next part of the video. Perfect. So I hope you have a good idea about what are relations, what are types of relations, what is mappings, what are functions, how to test for a function, what is a function notation, how to write domain and range, and we tested them out with some examples. So that was an introduction. Now we'll take many examples to master what we have learned. This is a very important topic, essential for students taking higher level mathematics. I hope you find it interesting and useful. Practice with the examples which are given in my website, and if there are any suggestions or comments, feel free to post your comments And if you like and subscribe to my videos, that'd be great. Thanks for your time and all the best.